everyone. Thank you for joining us today on Pi Day 314. My name is George Rivera, and I'm happy to be here with Han Tran from Fluke. She's an application engineer. While we're waiting for a few late joiners to the webinar, I'll give you a couple slides here about our company. While you may have visited our website and signed up for the webinar, let me just give you some background information about us. As you can see from this slide, on the left side, we have a wide variety of markets that we serve, and on the right side, many products. And sorry for the small font, but as you can see, it's quite a big variety, and it's not even a complete list. We also have on staff a variety of experts. For example, I'm an engineer specializing in process instrumentation, controls, and calibration. I previously worked at several chemical plants. If you visit our website and go to any department listing page, you'll see intelligent filtering on the left side like that of retail websites. It's pretty unique for an industrial distributor. On the right side of this slide, it talks about our internal portal, which we use to better serve our customers. Development of both was an investment of several $1 million and years of effort. We're also a stocking distributor and carry an inventory of millions of dollars. Let me introduce now formally Han Tran. She's an application engineer working at Fluke for the last couple of years. Prior to that, she spent over 10 years with General Electric's Bentley, Nevada Condition Monitoring Division and is a holder of 3 patents. She has a Master's of Science in Electrical and Computer Engineering from Georgia Tech. And thank you so much for presenting today, and I'll turn over control to you now.
Thank you for that introduction, George. I'm excited to be here today, especially on Pi Day. I hope everyone's enjoying some form of Pi, whether it's reading the entire series of numbers out or having an actual physical Pi. So we are here to talk about power quality and energy management, and some of the best practices that you can take as a, if you're a maintenance manager or maintenance facility tech. There's some sound coming through, George, just an FYI, like scraping sound. I don't know who's coming through on there. Cool, thanks. So got a quote from an anonymous smart person. They said, you can't manage what you can't measure, and that's very true. And we'll go through some examples of what we mean by that. Hey, George, there's some noise on the mic. Just an FYI.
Let me see if I can mute it. I'll find the appropriate control here.
Oh, thanks. All right. Topics we're going to cover here are, what exactly is energy and what is power and why you should care about energy and power. Then we're going to we're going to look at an example of an industrial facility and kind of break down the electrical system so you can see where you can identify opportunities of energy savings. We're also going to go over a little bit of the principles and theory behind energy and power quality. We won't go into too much detail on that end, and then I'll kind of show you what tools and software you can use to help you make these measurements. So first off, what is energy and why should you care? The profitability of a business can directly be affected by the electrical energy that's consumed by the facility. And because of that, it's important to measure energy use and make sure that the power quality meets local standards. Local standards in the United States will basically be EN 5160 or IEEE 519 if you're looking at Harmonics and the rest of the power quality. The rest of the world has other standards that are pretty similar, but they may have different titles and slight adjustments. The government has provided tax incentives, subsidies, federal electricity programs, loans, loan guarantees, and funding for research and development to promote the efficient use of energy resources. So an example of this, if we're talking about residential areas, is like Arizona's qualifying wood stove deduction, where if you replace your old existing wood fireplace with something that's more efficient, like a qualified gas-fired fireplace, then you get some kind of deduction for that. And then on a bigger scale, if you're looking at corporations, renewable energy property taxes is a big one. That's at the federal and business level. So that's when businesses use things like solar or fuel cells, wind or geothermal, any kind of renewable power source, the government offers tax credit or rebates. And you can get more information on details like that off of energy.gov. So measuring power quality provides a window into the health of the voltage supply and the load and how it's reacting, and if it's putting anything bad back onto the grid. And by maintaining the power quality to the right level, this enables businesses, facilities, maintenance teams to keep up and running, essentially, and avoid that unplanned downtime. So many companies monitor the cost of oil and gas, but the smarter companies are the ones that pay attention to their energy bill. So measuring energy is the key to putting yourself in control of that utility bill and of your facility. By measuring and looking at historical energy usage through the age of the facility and keeping track of this and understanding the rhythm for your plant allows you to make those adjustments, whether it's human adjustments, behavioral, right? Or whether it's operational, or whether it's actually replacing a machine with something more efficient. So measuring power and understanding the quality of your power is the key to ensuring that your plant runs less of a chance of being a victim of that unplanned outage. And understanding both energy usage and power quality is that 1-2 punch you need for maintaining a facility. You kind of want to do both. One without the other only gives you part of the picture. And all too often, energy and power are used interchangeably, and that's not really accurate. What is different? What is the difference between energy and power? What is energy and what is power? So we'll kind of review this quickly here. We know that 1 watt of electrical power maintained for 1,000 hours equates to 1 kilowatt hour. And what's interesting is if you have 1,000 watts maintained for only 1 hour, it's still 1 kilowatt hour. So keep that in mind. Basically, electrical energy is watt hours and power is watts. So that's one difference right there. So you can see there's a factor of time when it comes to talking about energy, whereas power only has wattage as its units. And power is the rate at which work is done. So if you're going back into your physics days, right, or thinking about physics, that's how fast you can do the work, or how fast you can move that little electron or the object. 1 kilowatt hour per 1,000 hours is 1 watt. So when you're measuring power, the purpose is typically to measure the quality. The factor of time is dependent on human behavior and operational factors. So how fast are you operating your machine? And is the motor sized properly for that operation, for an example? And the human side of it is, it's the behavior side. So for example, leaving the lights on, is it really necessary to leave the lights on when there's no one in the room? And then energy is the capacity to do the work. So in physics terms, it's what makes it possible to move objects, whether it's an electron down a wire or a car down the road. It's the required work. And if we know the strength of force needed to move the object, we know how far it will move, then we can calculate the energy needed. And then you can use that to trend. So the way I've divided this section really is between quantity and quality. And we'll go over what we mean by that and why it's significant. Quantity typically has units associated with it, like voltage or volts, amps, kilowatts, etc. Typical actions associated with quantified data are like performing load studies to figure out if it's possible to add more machines to your facility. Another action is to trend the energy usage and get an understanding of the plant rhythm or the heartbeat. And then understanding how and why your facility is using energy at certain times of the day allows you to take control of your utility bill. When you're doing this, you may look for improvements in your overall energy profile. So that's like figuring out the pattern of your energy usage. So if you see something, for example, you know your facility is closed down on the weekend, Saturday and Sunday. If you have a nice calendar view of your energy usage and you see that you have a steady power usage Saturday and Sunday, then you know that you can shut maybe or lower the AC or heat, right? Or some machine is on that doesn't need to be on. Now, when we're talking quality, it's not typically associated with the units. It's associated with characteristics like harmonics, dips and swells, transients, etc. The actions you would normally take when you're measuring power quality is to detect reoccurring issues like nuisance tripping breakers. You would also perform in-depth analysis and find intermittent disturbances. The purpose of taking these actions are really to reduce your energy bill, or sorry, it's your energy utility penalties actually, to either reduce them or avoid them completely, because who wants to get charged extra on their energy bill? We'll review some of these examples of surcharges that you can avoid on your utility bill and other reasons for taking power quality measurements, by the way, is to prolong the life of your equipment and, again, reduce your facility's downtime. So there's many consequences of not addressing power quality issues. There's power failures such as nuisance circuit breakers or trips or circuit breakers tripping or fuses blowing. LED indicators on drives have also been known to blow out. The other one could be, other consequence could be flickering lights. So exactly how you're seeing here, maybe the office lights even are flickering, and that can cause, human health issues, causing migraines or causing people to go into epileptic shocks. So that definitely want to avoid that. There's also consequences of breakdown or malfunctions of machinery due to overheating, and other things that are not as obvious are your computer's glitching. There could be times when your computer is acting up and it's actually due to power quality issues. Those are typically harder to connect, but there are certain tools that can help you measure your power quality going to your computer and figure that out. And so the need to oversize systems to cope with additional electric issues means you have to buy bigger machines. And so taking into consideration power quality will help you size your motors, for example, a little better. So this is a list of common causes of energy waste. This includes things like, so the first line, right? Leaving the lights on when there's no one home, or having machines run when you're not actually producing any product. It's a waste of money. The type of measurements to take in these cases are energy studies and looking at the energy consumption for every calendar hour, day, week, or month. And as mentioned before, picking up on the patterns, right? And the rhythm and the flow. An example solution to human and process efficiencies is to install light sensors, automatic switch timers. If no one's actually in the room for a certain amount of time, then the lights switch off automatically. The other example too is ramping back the AC or heat to a comfortable setting. I don't know how many times I've been sitting in the office in the summer and the AC is blasting and I'm freezing, and there's really no point for it to be on that high. And I'm not the only one freezing, right? The other cause or condition for energy waste is operating loads exceeding the utility peak demand. That means you're incurring, again, a surcharge on your utility bill. And in order to avoid exceeding peak demand rates, Performing energy studies and trending the power usage of your facility will help with that. You'll be able to figure out the right level load for your process, or if possible, move production to another shift that has lower peak hours. Another common cause of energy waste is worn or faulty loads, compressor air leaks, worn pump impellers, clogged air filters, for example. Clogged air filters will cause the motor to work harder to push the air through. So replacing the filters when replacing the filters at on a timely manner before they are so clogged that the motor is working so hard is a good idea. But there's also a balance. So you don't want to constantly be replacing filters unnecessarily. So that's where having a power quality tool, taking the measurements of that system will help you determine that sweet spot. And then performing energy studies and trending power exactly with that tool will help with that. And poor power quality can also cause energy waste. So things like harmonics, power factor, and unbalance are qualitative characteristics of power quality. So using the right instrument can help you figure out how to eliminate these issues. And then finally, incorrectly sized motors or inefficient aged motors can cause energy waste. There are instruments that will help you size your motor properly. There is an instrument that will also provide electrical power analysis as well as motor mechanical power, torque, and efficiency all in one. And you can also see the size of your motor and derate it per the NEMA derating guidelines. Now, these are a list of poor power quality. So you can see at the top, there's inductive and capacitive loads. For example, an oven element is purely resistive, whereas things like motor ballasts or motors, ballasts, and electronic devices are inductive or capacitive. So the measurement you would take there is the voltage and the current and the phase angle between the two. And then the solution usually is you would find out what exactly is the capacitance or inductance level, and then you'd purchase a power factor correction machine to put in line, kind of insert it in your circuit to fix and offset that phase shift. Another cause or condition of poor power quality are nonlinear loads. And nonlinear loads are, although they're growing more and more popular because they're more efficient with their energy usage, they cause issues with harmonics because they could possibly cause distortion and put that distortion back onto the power supply of your facility, and which then your facility puts back onto the utility grid, and then the utility will start charging you because of certain things we'll talk later, like power factor. So what people would do here is a similar fashion. They'd figure out what that harmonic signature looks like, and then they'll get something like a static or dynamic filter, basically an active filter, to insert into their circuit and compensate for any harmonics that those nonlinear loads are causing. Another cause or condition of poor power quality are loads improperly distributed across each phase. And what that means is in a three-phase system, you're going to want equal voltage, equal current on all three phases. And if you don't have that after a certain amount of inequality, you start to pull way too much current in one phase, which could cause overheating on your machine, or just your machine to stop running at all because it's expecting a nice balanced system. So then what you would do with that is, if, for example, if you had a bunch of test benches, if you're an engineering place, right? You had a bunch of test benches running on phase A, and you find that it's drawing a lot of current compared to phase B and C, you would redistribute some of your test benches, like physically move them or just plug them into a different side of the building to use up the other phases and not always be on phase A and load phase A to overload it. And then high energy loads turning on or off, causing voltage variation. So that's mainly gigantic machines, right? That when you turn them on, they might initially draw a lot of current. And so they'll cause a dip in your overall supply. Or when you shut them off, they'll cause a swell, because then all of a sudden this load disappeared, and now there's a huge the power supply that was compensating for that is still compensating and didn't shut off the compensation fast enough. So a solution for that would be to check the circuit load capacity and resize it. And then another is to adjust the transformer tapping. Transients are another cause of poor power quality. So transients, a lot of people like to describe them as spikes in your voltage or your current. They could be caused by switch contacts arcing or lightning strikes. That's a very common one, lightning strikes. They'll cause fast transients, which are sub-half cycle changes in your power. And then there's also oscillatory transients, which those are caused by your switch contacts. Solutions for that is either replacing the switch, so you have switches that are rated a little better so they won't cause any arcing, and then a good grounding system for all the like a lightning suppression system. So we'll review here some power quality and energy theory. I like to start out with the beer analogy. It's a nice visual. Basically, if you have a mug of beer, you're sitting at the bar, you really don't want to be drinking a lot of foam. You want to be drinking the actual beer. So you can think of the wasted power, or wasted power is really reactive power, and that's got units of kVARs. That is your energy that doesn't produce any work. It doesn't do anything, it's a waste. So your useful power is your beer, the liquid, where the work is actually doing something. And it's called real power, and the units are kilowatts. And then demand power is the total from the top of the foam down to the bottom of the mug. And that is the total power delivered by the utility. Usually that has units of kVA, kilovolts, apparent, kilovolt, I'm sorry. And there, if we think about the wasted versus the useful versus the demand, the wasted and the useful you can see is just a sum of the demand power. If you kind of, it's the sum of the total power. Examples of wasted power. If we were looking at a motor, for example, there's it has a rotating part, right? That rotating part, the actual rotation is the useful power. The heat that's being produced is your wasted power. So that's an example of a form of wasted power. And then the total power going to that motor to actually create all that work, which is also creating the heat, is your demand power. So kilowatts is pretty much the rate at which your AC energy is expended. Like we were saying, it's more like kilowatt hours divided by hours. So then the hours kind of go away and you're left with kilowatts. And watts measure the energy required to do actual work, such as running the motor, like we were just saying. And then put another way, working power, also called actual power, active power, real power, it's got a lot of names, is the portion of total power that performs that useful work, like turning the belt or a fan. And the pain point here is that maybe you just want to try, or I guess the consequence is energy waste, and maybe you just want to try and find opportunities and ways to reduce that energy. On the right is a screenshot of a graph from the Fluke Energy Analyze Plus software, and this is an example of the measured power of a three-phase system and its total power over a span of a few days. So all the different colors are the three phases plus the total. And so the point of looking at this is to understand, all right, I have a date and time stamp. Now my power is acting like this between this time and this time. Is that what I expect? You know, do I actually have product being produced, or can I just shut off the machine at that time and save some energy and save some dollars? Demand kilovoltamps. So this is reactive power is what it's called, and it's kVA. And kVA is the power which magnetic equipment such as transformers, motors, and relays need to produce that magnetizing flux. In other words, it's the total voltage and current required from the utility, regardless of its efficiency or whether it actually does any work. So really, technically, you can get a bunch of power from the utility and you can completely waste it. You can have a ton of foam in your beer and no really any liquid, which would be bad for your facility. So the consequence here, again, is you want to reduce the total demand that you're putting on the utility. And that's just your overall utility bill. So that's not even getting into the surcharges. That's just getting into, I just want to lower my overall power usage or energy usage, sorry. Power factor is interesting because it's, well, let's start off with a description of it. Power factor is basically a description of the efficiency of operation of your system, of your electrical system. So for example, if your power factor is 1, then you more or less have a system that is 100% efficient, at least from the utility's point of view. If your power factor is less than 1, there are losses in your facility, in your electrical system, within your facility that the utility has to pay for. So if you're a larger energy user, the utility gives you a better rate on each kilowatt hour used, but only if your power factor stays above a certain point. So usually that's, and it depends on where you live, but usually it's 0.95 or above, and you won't have to pay a penalty. And the interesting thing about that is if you are below 0.95 in our example, power factor, even if it's only for, a little while, you get charged for the entire billing period. You get that additional fee for your entire billing period. So it doesn't even matter if you only had poor power factor that was less than 0.95 for 15 minutes. You get charged for whatever that billing period is, was like usually month to month or on a 3-month basis, which can really suck. So consequently, these larger facilities will want to ensure their power factor stays above the 0.95 threshold. And to do this, they install things like power factor correction equipment. This monitors the power factor and automatically switches in compensation in line with the electrical circuit. And then to choose the right equipment, Fluke's power quality analyzers actually measure the consumed power and log the power factor. So you can decide on which equipment to install. And to measure real power, you also need a meter that can simultaneously measure voltage, current, and all the stuff mentioned before that lies in between over a 1-second period. It's a very it's a guide, it's a standard for all power quality measurements. It's got to happen over a 1-second period. And a digital multimeter can't really do that. I know a lot of people use digital multimeters and they'll measure each phase one after the other. And they'll do a bunch of calculations, right? Pencil paper calculations or Excel spreadsheet calculations to figure out their power factor. The nice thing about the Fluke power quality tools is it does it for you. And it does it for you in a way that makes more sense. It'll measure all 3 phases at the same time and your neutral at the same time. And yeah, that's enough about power factor. So Harmonics, when we're looking at harmonics, this is something that increased in the 90s because of the use of computers, and because computers are nonlinear, have nonlinear power supplies, but it's starting to decrease in concern, or hold steady in concern, because engineers are getting smarter and designing their products to cause less harmonics on the power systems. But people who are going to replace replace their lighting, like for example, all the office overhead lighting, which are usually fluorescent light bulbs, they're going slowly to LED. Now, if imagine a large facility, making that change, drastic change quickly and going over from fluorescent to LED, yes, you have just made your facility more energy efficient. However, LED lighting needs to improve on their harmonics because they can cause harmonics. So you can imagine switching from something that was pretty nice and steady power to something, yes, maybe more efficient, could actually cause inefficiencies, which is kind of funny. There's a balance there. So on harmonics, the image on the right is basically a bucket. So you see the three phases, black, red, blue, phase A, B, C, and you'll see THD, which is total harmonic distortion. And right now we're looking at the current harmonic distortion. And harmonics, so say you're, at least in the US, our supply frequency is usually 60 hertz. So if you have a second harmonic, it's 120 hertz, and third, it's, from there, it's 60 times 180 hertz or something like that. So this right here, this main bucket for one, should be your highest if you have a good power quality where there's no harmonics. You can see here that the third harmonic, which I think this was taken for 60 hertz. So at 120 hertz, you're experiencing some kind of third harmonic. And then at 180, you're experiencing some kind of harmonic here. Or sorry, not 180, it's 5 times 60, 300. I can't do math. Yeah, so the system isn't exactly clean, but the nice thing about this tool, this Fluke tool, is that it has the standard in it, and you don't have to figure out what should my harmonic limit be. It just figures it out for you, and it flags it for you in a different screen. This one just tells you your overall harmonic distortion. So the benefit, the consequences of having harmonics on your power system is having unusable power, wasting that money, and you're not actually providing or making any products, right, from that power. And then, yeah, you'll have failures in your neutral conductors, which, because of the way three-phase power works, your harmonics will, quote unquote, try and it'll show up, it'll manifest itself as a higher current draw in your neutral conductors. And so obviously if you have higher current draw in your neutral conductors, you have heat, and then eventually, possibly, you'll have failures down the line, physical failures, like maybe burnout or something on your neutral conductors. Your motors and transformers will start to run hot as well, and that'll decrease their efficiency, and it'll shorten that machine's lifespan. So the nice thing about measuring harmonics is you can move down the line of your electrical system to troubleshoot and figure out the culprit. So having this tool, moving it down your electrical system until you find the highest peak of harmonics, will help you troubleshoot. And this will go out, most of the Fluke tools, I think if not all of them, go out to the 51st harmonic. The other quality issue that can happen are dips and swells, and we kind of briefly covered it earlier. And what they are is when the line voltage is higher or lower than the normal, than the nominal voltage for a short period of time. According to the standards, which are built into the Fluke tools, they'll tell you when you have exceeded this higher or lower limit over that period of time, so that you don't need to think about it. You just hook up the tool and press go. So the consequences for dips and swells is, for dips, you could have intermittent loss of power. And you could also potentially damage your equipment. For swells, you could definitely damage your equipment if you're putting too much power into a machine that's not expecting that level of power. And then the benefit of countermeasuring this, obviously, so the Fluke tools, they'll count up the number of dips and swells in a system, and that'll help you figure out, okay, so this particular system is experiencing the most dips and swells. So we'd have the biggest benefit or return on investment, ROI, is to replace this equipment, and we'll start seeing our power quality improve. Transients, we touched on that. That's just rapid change in voltage or current. So again, it depends on the amplitude, as you can see here in this little screenshot of a tool. Depends on the amplitude, depends on the duration of your transient. And transients, I know a lot of people like to show the spike going up, but really it can be spikes going down as well. It's definitely bidirectional. The consequences here are you can cause breaker trips that lead to downtime, and you can also damage equipment. So the benefit of taking these measurements is to avoid that downtime and avoid damaging equipment. Transients are kind of squirmy problems because, we're talking about lightning strikes as being a good example of transients. Well, that only occurs during certain weather. So you kind of have to, I know a lot of people ask me, how long do you measure power quality for? Or how long should I have these instruments hooked up? And I said, well, it really depends on your application. If you're trying to figure out what's causing your transient problem and you suspect it's the weather, you have to hook it up until the next time you think it's gonna, you're gonna have lightning strikes. And even then, the lightning might not hit that point again. So it's really, it's tough. I'm not gonna lie. It's tough sometimes to track some of these issues, and it just takes time. So we've only got, I think, a couple more slides on these. So in Unbalance and Flicker are the next few slides. Unbalance is basically a difference between your 3-line voltages, so on your 3-phase system. And this can be caused by single-phase loads or phase-to-phase loads, and unbalanced 3-phase loads like welding equipment. And then the consequences of unbalance is that, let's back up. So at the simplest level, all 3 phases of your voltage should always have very similar magnitude. Voltage and or current unbalance will occur when 3-phase voltages differ in magnitude, or 3-phase currents differ in magnitude, or do not have the same displacement of 120 degrees from each other. And traditionally, I've seen people, they'd calculate it using the DMM. And I think we already went through that example, but the Fluke tool will just calculate it for you in one shot. So you're not standing there. The other thing about taking the measurements with a DMM is that power quality and energy can shift. So when you make your first measurement with your DMM on the 1 phase, and then you go to the next phase and measure, something in power quality could have shifted between the time you took the first measurement and the second measurement and the third measurement for your 3 phases. And so really you don't have an accurate picture of your power quality by using single measurements at a time, especially if you're trying to track down unbalanced issues. Kind of a rule of thumb, and I don't like rule of thumbs because I'd rather know the reason why, but this is just what I've been told, is basically any voltage unbalance greater than 2% is problematic for, I think, any electrical system. And for every 1% voltage unbalance, motor current unbalance is 3% to 4%. So what that means is it's worse. So you'd want to check the conductors to see if the drive has failed, or if possible, power the motor directly by bypassing the drive to determine if the drive is a problem. And then this measurement rules out the motor overheating due to voltage unbalance, but it doesn't, on the other hand, rule out overheating causes. So generally, current unbalance for 3-phase motors should not exceed 10%. As we covered in the voltage unbalance section, the voltage unbalance will cause current unbalance. And then properly diagnosing voltage or current imbalance has several immediate benefits, because a voltage imbalance can cause a current imbalance, and diagnosing a voltage imbalance can help avoid motors that trip current overload fault protection devices. So you can avoid elevated motor temperatures and long-term wear by diagnosing voltage unbalance specifically. And then flicker, this is the last slide on the theory here, is basically visible changes in the brightness of, say, your office lighting, for example, of any kind of lighting. And it's defined by a standard. It's got a definition, you know, like this is how long it'll last, and this is how fast it'll happen, and this is the amplitude of the voltage or current, and etc. And flicker can be caused, you know, in those old horror movies, when you turn on your electric arc furnace, for example, or just basically when a large motor is starting, or so that would be like welders and boilers. When they start, they can cause flicker. And we covered, you know, health issues on that end. That's why we look at it. And honestly, I think in the US, we don't tend to pay attention to our health too much, so it's not a huge concern, flicker. But flicker can also cause not just health issues, it can cause nuisance tripping. It can also cause unwanted triggering of your backup power supplies, and may cause you to drain your batteries on your backup power supplies, because the UPS will be switching on and off. And then some electronic equipment is sensitive, such as the electronic equipment in hospitals or medical laboratories. So the benefit of measuring flicker is avoiding those situations, and then also pinpointing what equipment is causing the flicker issues. So now we're going to go over kind of an example of what a facility would look like in terms of its electrical subsystems, its electrical distribution, and guide you towards where and what measurements you'd want to take to find the energy saving opportunities. So we're going to focus on 3 building systems. The first is electrical subsystems, and we'll actually just go over electrical subsystems. I want to briefly mention the other 2 systems, which are the production process systems and the building infrastructure, or what we call kind of like the building envelope. So within a facility, there are multiple ways you can save money on your energy bill. And the product or production process systems includes examining mechanical loads and optimizing compression and steam systems, whereas the building infrastructure improvements include optimizing things like ventilation, heating, cooling, insulating your building properly so it actually holds in the heat when it needs to, or holds in the cold air when it needs to, and basically shutting the doors, right? Not leaving the windows open. We talked about replacing your inefficient lighting, like your fluorescent bulbs, with LED lighting, but doing that carefully so you don't cause harmonics on your system by trying to be more efficient. And then electrical subsystems here on the left, that takes into account your utility power, and it makes it usable. It makes the power usable by the rest of your facility. So it converts that it converts, well, I guess I should say this. So if your building is big enough, you'll likely have a substation on premise, and that will convert higher energy or power from the utility down to something that is usable to your facility and the machines in your facility. If your building is smaller, you likely just have a main service entrance, and that will distribute the power directly from whatever substation, whether it's an on-premise or whether it's a substation owned by the utility. It will distribute it throughout your building for usage. So things like motors that plug into 3-phase power, right? Or even your computer that might plug into a receptacle in the building at 120 volts. So since the electrical subsystem supports the other two, we're gonna just dig into this, and this is where you'll primarily use your power quality tools. It's kind of a lot to see, but hopefully you guys can see my arrow. So this main service entrance here that I'm circling is where you would start if you wanted to verify how much power your facility is using overall. So that would be your total power consumption of your facility. And if you are trying to figure out which circuit branch, so each of these 4 branches, this is just an example, you might have many more branches or fewer. Each of these circuit branches consume a fraction of that total power that you might be measuring right here with a Fluke power quality tool. Now, the main goal when you're doing energy waste management, right, is to figure out, hey, where are my biggest energy hoggers? And is it something that really needs to be an energy hogger, or can we replace it with a machine that is more energy efficient? Now, the idea behind that is you want to pinpoint your biggest energy hoggers and provide your the kind of the people that would be approving the purchase of a more efficient machine, provide them with justification, right? Like saying, okay, this motor here, motor number 1, is using 60% of our facility. This is being an exaggeration. It's using 60% of our facility's power because it's really old and clunky and it's not efficient. We need to replace it with a more efficient energy efficient motor. And our Fluke power quality tools will tell you exactly the dollar amount that you would be saving by switching to a more energy efficient tool. So that's kind of the idea behind measuring at the total and then measuring down here near the motor and then measuring at motor number 2, saying, oh, motor number 2 only uses 10%. So that wouldn't really be a priority in replacing with a more efficient motor. This would be a priority because it's using 60%. So it both provides you with ROI and it also provides you with, I'm talking about the Fluke tool, it'll provide you with your return on investment and it'll provide you with which one should you be looking at? Where should you be looking for energy savings? The other one, which is very common, we've brought up a couple times already, is if you measure here at the sub panel, that maybe this sub panel is dedicated completely to lighting. You can see how much energy your lighting system uses. So then that will justify, hey, maybe in this case, we'll switch out the numbers. The lighting is actually using 60% of our energy. And guess what? They're those older style fluorescent bulb lighting. Well, if we go to LED lighting, this is how much money we'd be saving. Same with anything else like servers or your printers or computers and whatnot. With motors specifically, there is a Fluke power quality tool that does motor mechanical measurements. As in, you hook it up to the nearest circuit breaker or the drive that might be driving that motor, the like VFD, variable frequency drive, and it'll measure the torque. It'll measure the efficiency. It'll give you a lot of motor information, and it's live motor information while you're operating. So in that sense, you can tweak your operations, and by tweaking your operations, you could possibly get some kind of energy savings from that. So that's another way you can do it. And that's getting down to kind of, I would say there's probably 3 or 4 different levels of energy savings hunting. So level 1 is just making sure that your building envelope is good. So, and your human behavior is good. So please shut the lights off or install automatic sensors for the lighting, or please shut the window or the door. We really don't need to leave it open. You're letting the heat out or letting the AC out, whatever. And then the second level would be, all right, now let's take a look at which machine is using the most energy. And then the third level is looking at your operations. It's how can I tweak my operations? Maybe there's a chemical, like in a plastics facility, maybe there's a flow rate that is more optimal. It's like running, so I like to use the car analogy in this. It's like having a car that has a speedometer that goes all the way up to 200 miles per hour. It doesn't mean you should be running it at 200 miles per hour all the time. One, that's unsafe, around here at least, and in the city. And then two, it will wear out your car. So there's a sweet spot for your car to run. And usually, what do people say? It's usually like 60 miles per hour or something like that. So that's what the power quality tools are doing. They're helping you find the sweet spot for your facility and for your machines. We talked a little bit, we keyed in on the utility bill quite a few times. So why does the utility bill matter? Well, one, you need to know how much electricity costs to use at different points at different points of the day and year. Two, you need to know whether you're being penalized for peak demand or a power factor issue. And peak demand issue, by the way, I forgot to cover that in the theory. That basically means, and it depends on where you are, it's very regional and even country specific. So for example, over a 15-minute interval, how much power are you using? They average it out. And if you are above that average, then you have gone beyond your peak demand with that utility and you will be charged a fee for that. I think, I don't want to say for sure, but I think our facility is averaged out over 15-minute time span. And then to give you an example, other countries might average out over a 10-minute time span. So it really just varies. You got to read your utility bill. And then these bills, like we were saying, vary from utility to utility and from location and will depend on the contract that you have. And the type of contract applicable to your facility will depend on the quite a few numbers of factors, like the total amount of energy that your facility is going to consume, the voltage level of your connection, and the rate at which your utility is going to be charging you. And in this typical bill, I've been told this is the bill at our facility over here in Everett, Washington State. So there are charges for peak on and off. So you can see here there's an on and an off. And basically that just means the time of day, right? So this doesn't have the hours listed on here, but for example, maybe from, I don't know, 6 a.m. to 6 p.m., that's when you have an on-peak time. And an off-peak time would be, hours out of before 6 a.m. and after 6 p.m. And utilities do that because, you got to make money as a utility, and you're going to charge people more when there's more demand for it. Whereas if there's less demand, you charge less. And that's kind of the secret. So if you're able to move a shift, majority of your power usage to an off-peak time, that's one way to save on your energy bill, is to move it to that off-peak time. And then once you have the data, which shows where and when the energy is being used, think about the wastes from the system incorrectly installed, like temperature setting too high or unnecessarily long cycle times between discrete processes. Then looking at power and energy profiles from a period that covers all possible operating cycles. So you want to look at your hourly, daily, weekly, whatever is most applicable to your facility. And that'll reveal the peaks and troughs of your energy use. And it'll show you where energy is being consumed when no useful work is being carried on during, for example, evenings or weekends. And it's important to compare these profiles against your known operating cycles and working time, because I've received questions before of, well, how long, I think I mentioned this, how long should I be measuring? How long until I know to stop measuring and then look at the data and figure out my energy usage? And I say, well, it really depends. It depends on your operational cycle. So you want to cover as much of your operational cycle as possible. I've actually talked with a guy where, when it's in the colder weathers, they operate more efficiently because they generate a lot of heat. And if it's already cold, they keep the doors open and it naturally cools, right, the building. And when it's warmer, they kind of tune down their operations in that sense. And so it really depends. Even over a span of a year, something can change in your operations. You want to capture that. And I know saying saying measuring for a year maybe wouldn't be too realistic if you want a return instantaneously, but just at least capturing where you'll have the biggest change of your operations. And then we talked about power factor. So this is just the penalty for having poor power factor put back on the grid. And the reason why, and then also the demand for the billing period. And the reason why you get a surcharge for these is because the utility now has to kick on another machine to either compensate for your poor power factor or your demand being higher than what you guys agreed to on your contract. And then I know we're running out of time here. So really briefly, going to go over the tools and techniques that you can use to identify areas for improving energy usage. I'm going to skip that. So an idea here, like we were talking about before, you'd have one unit at your what is it called? Main service entrance. And then you'd have another unit possibly. So you'd have two total. You'd take this one and you'd move it from, for example, your augers and your pumps, and you'd move it to, say, down the line, down the electrical line, the power line, to your robotics, your PLCs, whatever's controlling your robotics. And then maybe you move it down to the VFDs and the motors. You do this so you can see, all right, where is the energy usage? This right here at the main service entrance will give you your total, whereas this will give you your fraction, and it'll let you pinpoint, all right, where is my biggest return on investment? Hey, if I replace this motor because it's sucking up a lot of power, it's sucking up a majority of power on this electrical circuit, then that's my biggest payback. And then this is a view, a calendar view, basically Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, over 4 weeks, over a month time span. And you can see here there is energy usage on Saturday when there shouldn't be. And it's a quick, nice, easy way to say, hey, there's something up here. Let's go investigate. And then this is like a nice little dashboard that counts up the number of events, like the number of dips and swells and flicker and all that occur. This tells you that your frequency is good if it's green, and this is your 3 phases for your voltage variations. And you can see here phase A is over per the standard EN5160. So it's this screen basically is your first pass at power quality if you don't have a clue of where to start. And not just power quality, but energy analysis, right? If you don't have a clue of where to start, you start in this mode, you hit go, and let it go for as long as it makes sense, right? Maybe you know of 3 different operational cycles. You let it go through all the 3 of those operational cycles, and you see red means you should probably check it out. Green means you're okay. The events bar will always be yellow if there's any kind of events, and you can actually drill down into detail to what the events are. And this is a screen of how you can drill down on the events. This is the Sabima curve that tells you if you're within tolerance or not. One other really quick thing that I wanted to show is this is don't go away. This is the, get rid of tables. Here we go. So this is the actual software. Hopefully it's coming through all right. And we basically have 2 data sets that we're looking at, the red and the green. And what's nice about this software is, let's say you are wanting to optimize, 9 a.m. or no, what's this example? 5 a.m. You shouldn't be having any kind of power, and you want to compare it to 9 a.m. What's the power usage there? You could basically do that. Now, if you wanted to compare to 6 a.m., you can basically slide it over like this, and you can compare your software. You can compare your 2 data sets. Pretty powerful tool. Or you can lock it with this locking tool and slide them both at the same time. But I think we're out of time, so want to leave a little bit of time for questions here. So George, you want to open up for questions?
Hi, everyone. Yes, please use the chat feature and ask any questions. Thank you, Han. It was a very good presentation. Appreciate your time.
Thanks for the opportunity.
No problem. Okay, well, here's the first question. How can you get torque and other mechanical outputs from just measuring the voltage and current?
Oh, good question. All right. Our tool, the Fluke 438 Series 2, measures by using just voltage probes and current probes, and it uses current signature analysis from the current and the voltage that it measures to determine what the torque is. So it uses a very complex algorithm to figure this out. So you don't have to make any, physical measurements at the motor itself. Like if you want to measure torque nowadays, you'd have to take your motor apart, put a torque sensor in, put your motor back together, and then run it. And usually that's on a dynamometer in a lab somewhere. So you would have had to ship your motor off somewhere to do this. And it's fairly expensive and fairly complex. Whereas with the Fluke 438 Series 2, you basically hook up to the VFD, or if it's not operating on a VFD, just hook it up to the closest circuit breaker where it's getting power, where the motor's getting power, and collect the voltage and current there, and the tool will tell you what the torque is and the efficiency.
Okay, another question from was one of the slides said the 1736, 38, 43 series. There's a lot of different models, and how do you know which one is which? Let me just say, I'll let you answer as well, but that's what we're here for, is we got to review the application. It's hard to really determine it on your own if you can get lost in all that literature. So might be better to give us a call here at T Equipment, and we'll be able to help you for your specific applications. And I don't know if you wanted to add anything, huh?
Oh, yeah, absolutely. Reach out to T-Equip to talk with them about your specific application, and they'll pull in, me or our really good tech support team if there's some very in-depth questions.
One other housekeeping thing, someone was asking about the slide deck, if it would be available afterwards, and yes, we'll give you a web link to download it rather than sending it as an attachment, so it gets stuck in your spam folder. That'll go out in an email tomorrow, and I'm recording the session, so hopefully we'll be able to send you a link for that as well, assuming everything worked correctly. One other question, how can you tell if a power quality is good or bad?
Yeah, so as mentioned in the slides, there are standards that each region and country goes by, and so you'll have to go per your local standard. And in the U.S., typically it's something called EN 50160. I just call it EN 5160. And most of the Fluke power quality tools have kind of an easy mode, where if you put it into this mode, it'll set all the limits for you per that standard. And then if there's anything that exceeds that limit, whether you have a rapid voltage change like a transient, or if you have a dip in voltage or current, or if you have harmonics, then it'll visually tell you by alerting you, hey, red, that bar is red or whatever. If it's green, it's okay. And so that's how you can tell if your power quality is good or bad, is just put it into kind of that easy mode on our tools.
Okay, that's basically all the time that we have for the session. Again, everyone, appreciate your time and look forward to hearing from you. You can reach us at the sales team at T Equipment email or the phone numbers that are on the screen. Myself and there's a couple other guys here that are trained in handling power quality questions. Thank you again, everybody. And thank you, Han.
Thanks,
Appreciate
everyone. Yeah. No, thanks, George. Bye.
Thank you. Bye-bye.